Hey everybody, this next video lesson is to cover something called the rate determining step for chemical reaction mechanisms. An important observation to make is that not all elementary steps occur at the same rate. Some elementary steps happen faster than others, but when you're comparing them, all you really know is which one's fast and which one's slow. To illustrate this point, I'm going to draw out a couple potential energy profiles. These potential energy profiles once again measure energy on the vertical axis and time along the horizontal axis. Basically, it's going to be a graphical representation of the energy of the reactants and products. It's also going to show us, as you remember from a previous video lesson, any point in which an activated complex forms. So here's what option 1 looks like. What you'll notice is that it has two bumps along the potential energy profile, which means that this reaction is going to happen in two elementary steps. Basically, the number of bumps that you see equals the number of elementary steps. What you'll also notice is that the elementary steps actually are slightly different heights. This one is taller than this one. If you measure the distance between the reactants as they begin, and we'll label this right here as the R for reactants and P for products, where the reactants start, the energy at which they start is high when it gets to this point. This is activated complex 1. This point right here represents the stage in the reaction in which the intermediate forms. Remember, an intermediate is that stuff that gets produced in reaction 1 that gets used up as a part of reaction 2. Went ahead and labeled those 2 points on this potential energy profile. Now, the last part that I want to point out is this second bump, which represents the activation energy for elementary step number 2. A couple of things that we can conclude about this first reaction, option 1, and that's, first of all, if the activation energy is large, that elementary step is considered to be a slow step. We don't really assign a time for that slow step. We just say that it's slower than the other steps in the reaction mechanism. So when you compare the two reaction mechanisms, activation energy 1 and activation energy 2, the bigger of the two is considered to be the slow step, where the smaller of the two is considered to be the fast step. In a reaction mechanism, the slow step is considered the rate determining step because the reaction depends on that slow step occurring. Once the slow step occurs, the reaction pretty much finishes. The first step is slow and the second step is fast in comparison, then the reaction's kinetics overall is determined based on that one rate determining step, the first step of the reaction mechanism. The other one is considered to be fast, so fast that the reaction depends only on the first step and not the second. Now, as you'd probably predict, option number 2 is a situation where the speed of the steps is put in reverse. So let's scroll over to give myself a little bit more room to make my sketch. Both of these reactions start about the same height for reactants and end about the same height for products. But the step 1 to create that first activated complex is much smaller than step 2. Now, I exaggerated those two heights to make the point, but the first step is fast now, and the second step is slow. Now, I apologize if you hear any noise in the background, but I am indeed making this while I'm getting my car fixed. I'm getting an oil change, so you just have to deal with the mechanical noises in the background. Now, if I were to label the two steps of this chemical reaction mechanism, activation energy 1 is the fast and energy 2 is the slow. And since energy 2 is the slow, that is the rate determining step. Now that we've seen what the rate determining step looks like graphically, let's talk about the rate laws of chemical reactions that happen in multiple elementary steps. The fast step and the slow step are going to help us determine the overall rate law of a chemical reaction. Just a general chemical reaction that occurs in 2 steps. We've got A moles of A plus B moles of B gives you D moles of D. Well, here's the first elementary step. You've got the A and the B making C, but the C, as you can see, gets immediately used up as part of the second reaction mechanism to give you D. So if you add up these two reactions, the C gets used up or produced and then used up. So my final reaction, as you can see, matches the overall reaction that you observed at the very top. Down here in blue, what the observed experimental rate law for this overall reaction looks like. And this is what it shows. The rate is dependent on K times the concentration of A promoted to the A power times concentration of B promoted to the B power. I just want to point out that it's a coincidence that it happens to match the stoichiometry of the overall reaction. But remember, an overall reaction, the rate law for an overall reaction can only be determined through experimental observation. Now what we're going to do is actually jot down the rate laws for each of the elementary steps, because we're going to use those rate laws to actually determine or prove the rate law of the overall reaction. We base the rate law off of the first reaction as K1, so that K is for the first reaction, and rate 1 is for the first reaction. You got A to the A power and B to the B power. We talked about how the rate laws for elementary step is based on stoichiometry of those, but not so for the overall reaction. Now, rate 2 is for elementary step 2, as you can see, and it has its own K value. That's based on the concentration of C promoted to the C power. Just a reminder, I jotted in the relative speed of each of these right after the rate laws. This is the slow step first and the fast step second. Observation I want to point out to you at this point is that the rate law of the first elementary step is the same as the rate law of the overall experimentally observed reaction. And that's not a coincidence. Because if you think about it, if the slow step is the one that determines the speed of the reaction, then it makes sense that the overall reaction is dependent on the slow step and the rate law of that slow step. So in summary, if you know that the first step is the slow step, then you can say that the rate law of that slow step is equal to the rate law of the overall reaction. This is something that you can count on without fail anytime you see slow step first. Now I'm going to point out at this time that this indeed is the easier of the two situations. Option 1, when slow step is first, is by far the easiest one to work with. We're going to do option 2 now, and I need you to pay very close attention because there's going to be some algebra and some substitution that you need to pay close attention to.